Hi there. I'm going to show you a few flawed grounding strategies that are extremely persistent in the electronics industry. They're so persistent that I was also seduced by one of them for the better part of 20 years for audio electronics. It wasn't even the case of I should have known better. I knew better, but I still fell for one of them. So let's get started. So the first example I want to talk about is star grounding. This is the one I fell for over 20 years. I know it's so hard to get good personnel these days, right? In audio, everybody says this is the holy grail of grounding. However, I found out that this is really not the case. So what makes this grounding strategy so compelling? Well, let's have a look at an example circuit. So this is a 30 MHz filter. I've been using it more in this series. If you want to know more about it, please check out part 1 and 2. Signal comes in here and comes out here filtered. Now it has a number of ground connection, and the whole idea of star grounding, you can already see it here. This looks like a star. Each ground connection has its own wire to the central grounding point. And this is a lot like my rule number 2 for good grounding. Give each ground connection its own via. The advantage is you have no crosstalk. The big disadvantage is the way it's done here with traces instead of a ground plane, it only works for DC. So let's have a look what happens when we compare it to the ideal competitor, a real ground plane. So here we see the layout with the ground plane and with the star grounding that we just saw. Let's first have a look at the RF performance of this circuit, and then later on we'll circle back to audio. So the first thing is crosstalk due to common impedance. If current is going through these capacitors and goes back to the ground, multiple current sources will go through this wire. So this wire is a common impedance that'll cause crosstalk. Second, you have a very inductive ground. We've seen in part 1 of the series that thin wires have an inductance, so for high frequencies this will not be a short at all. Third, you make large current loops, because the current loop will be like this, for instance, for the first part of this circuit. For the second part of the circuit it'll be like that. So these huge loops also add a lot of extra inductance. Thirdly, it's very sensitive to interference. As I've said many times before, if you make a loop, it's a perfect antenna for transmitting and receiving. So you're also transmitting interference right now, which is absolutely not what you want to do. And these loops will talk to each other. So if you look at this loop, for instance, and this second loop, these loops are within each other. So they will be like a transformer. So that'll also greatly reduce the performance for radio frequencies. Now let's compare those exact same elements on the layout with a ground plane. So crosstalk, you can see that there is a plane for the return current, and planes have the lowest impedance from DC to infinite frequency, or how far as you can go. So that'll be greatly reduced. Your ground will not be inductive at all, as it's the same point. Ground planes have the lowest possible impedance. The return current loops are incredibly small because the forward current is going here, for instance, and the return current goes right under the trace. So the size of the loop is basically determined by the thickness of your dielectric. So because the loops are far smaller, they will be far worse antenna. So you're transmitting a lot less interference and you're receiving a lot less interference. And since those loops are very small, they won't also talk with each other as good as in this example. So on all accounts, this is a far better solution for RF. So now let's circle back to audio frequencies. If we only had low frequencies in our audio designs, this star grounding would work perfectly. However, if you're building a DA converter, the output of a DA converter contains a lot of RF noise. So if you do not design the amplifier behind there as an RF amplifier, it will not work because you will not suppress those higher frequencies. Now, if you're building an amplifier or a preamplifier, you think you'd be safe. However, these devices have long cables connected to them in the form of interlinks and loudspeaker cables. Now, these cables are excellent antennas and they pick up everything like Wi-Fi and mobile phone signals, etc., etc. This will get into your circuitry and demodulate in your amplifiers. Now, the best way to get rid of those or to minimize the effects is to design all your audio circuits like RF circuits with a ground plane, and that'll reduce this effect the most. So this is the reason why you have to design your audio devices like RF devices. Otherwise, this interference will get in and reduce your audio quality. So another popular flawed strategy is the use of multiple ground planes. The idea is that you have, for instance, a digital part in your circuit, you have an analog part, and you give each of those a separate ground plane. And the idea behind it is that the interference cannot get from the digital to the analog. So what I've drawn here is a signal source in the digital domain and a receiving device in the analog domain. You can replace this with anything, any kind of chip or device that sends a signal and receives a signal. This is just to be able to make a layout, an example layout. And somewhere at some point, those two ground planes are connected with each other. So now what does the layout look like? Well, it could look something like this. On the left side, we have the digital domain. On the right side, we have the analog domain. And we have the 0 ohm resistor connecting these two. Now the obvious problem is the ground return current. Let's assume a signal leaves from here and goes to the right. The return current will have to go all the way up here, go through the 0 ohm resistor and go all the way back. So what you get in reality is this inductance between the digital and the analog ground. And that is going to cause a few problems. First, you get a huge return current loop, as I just showed in the previous slide. So this means you're becoming very sensitive to interference because you basically build a huge antenna. And you're also going to transmit interference. You're starting to get the drill here if you see more of my videos. The other thing is you're injecting RF noise onto the signal. Now let me explain this. So there is a clear impedance between the digital ground and the analog ground. This means that high frequencies will cause a voltage difference between these two grounds. That means it basically gets added onto the signal. So this signal will not only contain the wanted signal, but it'll also contain this potential difference between these two ground planes. And that'll cause a current to run in here, an RF current that you really don't want. So what you tried to do is to prevent interference going from one plane to the other has actually failed. It now goes right into your signal, which is the last place where you want it. Let's explain a little bit about common mode interference. Basically, you always have common mode currents running in your board, almost always. And this is going to run through your ground plane. Now, let's assume there's a common mode interference Wi-Fi signal, because everybody has Wi-Fi, going through this ground plane. As it travels through here, it gets to this obstruction and it's going to look for a way out. Now, this device will have some capacitance from the ground towards the signal line. There will always be some parasitic, and it will also be here. So it'll choose to go through this RF line. So common mode interference, which would normally stay on the ground plane, is now being injected to your signal as well. So this is a big problem. And this is the reason why multiple ground planes are always a bad idea. So I want to explain a little bit further why a single ground plane is not a problem. And I'm going to do that with the main board of my latest high-end DA converter. So this is the entire board. So I'm marking here with my mouse pointer the digital part. So this is the digital part. We have one DA converter chip here, another DA converter chip here. And this area is for the right channel. And this area is for the left channel. Now, if you've seen video 1, you've seen that I've proven beyond reasonable doubt that return currents stay under their traces. So since all the left channel traces are located in this block, all the return currents will stay here. So all the ground currents for the left channel will stay under the left channel. The same is true for the right channel, and the same is true for the digital. So if all these currents stay under their respective areas, then they will never interfere with each other. That's why this works so wonderfully well. So the next sneaky layout error I want to talk about is something that I call the via wall. I came up with that name myself. So this is my favorite stack up. You have the top layer for traces, inner one for ground, inner two for traces, and the bottom for ground. And the nice thing is that if you move from your top trace to your inner two trace, the ground return can stay on the same trace, because this layer is electromagnetically bounded to this layer, and this layer, this signal layer, is also electromagnetically bounded to that layer. Another nice advantage is that signals that go on the inner two layer are shielded between two ground planes. So a lot less interference will be able to come out. Now, if your design gets more complicated, you can turn the bottom into traces or power, or a combination of traces, power, and ground. So what's the idea behind the via wall? The basic idea is I'm going to put my signals on an inner layer as fast as possible so they cannot interfere anymore, and I solve all problems. Whenever you find yourself thinking that you have a really smart idea when it comes to grounding or interference, that's usually the moment you make an error. And this is a typical example of it I've seen many times. So what's going on here? You have a data bus, and you need to move this data bus from a top layer to the inner two layer, and you do it like this. But I think you're already starting to see the problem. You've cut up your ground plane basically. So a signal going here, the return current will have to go all the way around on this way or all the way around on that way. So that means the usual stuff. Very sensitive to interference, you're transmitting interference, and your signal integrity is reduced. How do you solve this? Well, this is the obvious solution. You move these vias apart so you have ground in between. And the great advantage is here, as I said before, the return current can stay on the same plane. The signal hops over from the top layer to the inner two and maybe a bit further down the road go back up, and the return current can stay on the same plane. And in this way, the return current paths are extremely short because the current only has to go around the via hole and then follow the signal. So this is probably easily more than 10 gigahertz bandwidth that you're talking about. Now, what if your stack up gets a bit more complicated? Assume you want to go from the top layer to the bottom layer in this stack up. So you have two ground planes. If your stack up becomes more complicated, you need multiple ground planes on different layers. You have to make sure that you tie them together with enough vias. And in between you have some other layers. The issue here is the signal moves here, goes all the way through the board to over here. But the return current was on this plane. It has to go to that plane. Now it cannot get there unless you place vias very close. So this is the solution here. These extra ground vias will make sure that the return current path can move from this ground plane to that ground plane. And if you need to move back from the bottom layer to the top layer somewhere on the right of the board, you'll need to do the same structure in reverse. So this is a way to deal with that. The next very common grounding problem I want to talk about is module pinnings of digital modules. So for instance, you have an ESP board or an AVR board or a PIC board. This is generally what's being done. On the left bottom side, you have a ground, and on the right top, you have a supply connection. Well, I guess you are starting to get the drill by now. So if you have a signal here, for instance, going to a port, then the return current has to go all the way to this ground pin and all the way back. One of these ways is on the module, which is mounted on top of here, as you can assume. Large loops, huge inductors in the ground, you're transmitting interference, you're receiving interference, you're bad signal integrity, and in general, you're having a bad day. Now, not that there's that much you can do about it if you buy these modules. However, if you make modules yourself, of course, you have all the freedom to solve it. So what could you do? Well, there's a stingy, smart solution: abuse a VCC pin. So let's assume on the module you place a capacitor very close to the connector. This is the connector for this single pin. So in this case, this pin between the main board here and the module here. So I haven't drawn all the other 39 pins, or how many of they are. You place a 100 nanofarad capacitor connected to the ground very closely, like I've drawn here, as close as possible. You do the same on the module. I've drawn it somewhat here in a cross section, and let's assume the ground current is moving along this plane. It can go up, go through the capacitor, which is a short for AC signals, go through the connector, go through this capacitor, which again is a short, and move back to the ground plane. So that means that you're using this capacitor as an extra ground return path, or basically two capacitors and extra ground return path. So that really all halves your problem. Now, of course, there are better ways to solve this, and one of them is simply to use more ground pins. This is what I did on the FPGA board that I showed in my previous video. I did a comparison between an off-the-shelf board and a board I made myself, and the one that I made myself had a lot less interference. This is one of the things I did. So the more ground pins, the better. So what's then the ultimate solution? Well, we see that on the right here. You give each ground pin, each signal pin, its own ground pin. And this way you ensure that the ground return path will always be very short and you have perfect signal integrity and minimum interference. So now I assume you're watching this because you want to learn electronics and prevent these kinds of mistakes. Now I have three options I can offer you. You can watch all my movies. They contain very simple rules, and I guarantee you if you don't use these rules yet and you start using them, your designs will improve overnight. Now you can also go a step further and download my free checklist. It contains 30 years of my experience. So the third option is to join my course. I don't have the course at the moment. I'm going to make it somewhere at the end of this year. And this will basically be my free checklist, but then turn into a professional program. So I hope you enjoyed this video. If you haven't seen anything else of me, check out the links in the description. I've got some great other videos as well. See you next time.
Bye.